In this video, we are going to study about eigenfunctions and eigenvalues. If you have an operator operating on a function and that gives a constant and the same function back, that would be an eigenvalue equation. And the function would be called eigenfunction, and the constant would be called eigenvalue. Let us take the example of Hamiltonian, which is a total energy operator operating on function xi to give E, which is a total energy values, times the same function xi. This would be an eigenvalue equation. In this equation, Hamiltonian is the total energy operator and xi is the eigenfunction and E is the values of total energy. So, in an eigenvalue equation, we have an operator operating on a function and that gives eigenvalues of the observable. In this case, the observable is total energy times the same function back. Identify which of the following functions are eigenfunctions of the operator d by dx. E power ikx, kx, e power minus ax squared, and coskx. For the function to be an eigenfunction of the operator d by dx, we have to operate d by dx on the function and see if it gives back a constant and the same function. So, let's write d by dx, which is the operator, operating on the function e power ikx. That gives us d by dx operating on e power mx would be m times e power mx. Applying the same formula, here we get times e to the power ikx. This is of the form operator operating on a function and that gives constant times the same function back. So this is an eigenfunction. Let's do the next example. D by dx on kx. K is a constant, so d by dx operating on kx gives us k. We do not get the same function back, so this is not an eigenfunction. Next is e power minus ax squared. D by dx on e power minus ax squared. Minus 2a x times e to the power minus ax squared. So we do not get the function back because we get x e to the power minus ax squared, and x is not a constant, so this is not an eigenfunction. Next is d by dx of cos kx, which is equal to minus k sine kx minus k times sine kx, because by definition d by dx of cos nx equals minus n times sine nx. So this is also not an eigenfunction. Is the linear momentum of a free particle with wave functions xi of x equals e power ikx and xi of x equals e power minus ikx eigenfunctions? The linear momentum operator is defined by minus ih cross d by dx. So let us apply here minus ih cross d by dx of xi x equals minus ih cross d by dx of e power ikx, which will be minus ih cross, the derivative here would be ik, since ik is a constant, times e power ikx. I squared equal to negative 1, so we get h cross k e power ikx. This is of the form h cross k xi, and so we got the wave function back when we operated the linear momentum on xi, so this would be a eigenfunction. Part B. Let us operate the linear momentum on xi. This time xi equals e power minus kx. Linear momentum is ih cross negative ih cross d by dx, which is equal to negative ih cross d by dx of e power minus ikx. D by dx of minus ikx would be minus ik times e power minus ikx. I squared is negative 1. We get minus h cross k e power minus ikx. Again, this is of the form the linear momentum on the wave function, giving us a constant times a wave function. So this is an eigenfunction.